Thank you, and welcome to the Xilinx Developer Forum. We have a packed agenda today with 3 parallel tracks that are aimed at making you, the developers, more productive. Throughout the day, you will hear from experts and customers like you. During the break, you can talk to the Xilinx experts who are wearing gray shirts, and they will be standing at tables that are marked with their domain of expertise. And you can also check some of the partner demos we have out there, which cover the entire development stack and will help you get the most out of our technology. As for the 3 tracks, we have a hardware designer track, an application software developer track, and an embedded software developer track. The hardware designer track is aimed at making the hardware developer more productive with Vivado and higher level design methodologies. We used to call that Club Vivado, and I'm just curious to see with a show of hand who has attended a Club Vivado in the past. Okay, that's about a third of the room, which is great because based on popular demand, we have added 2 other tracks, the software and embedded software developer tracks. The application software developer tracks is focused on how to program FPGAs and Zinc SoCs in a familiar software environment. And the embedded software developer tracks really target the design challenges of heterogeneous SoCs. There we will cover industry and open source initiatives to address those challenges. And more specifically, we will give you key insights on our work with the Zen hypervisor, embedded Linux, multimedia framework, and interprocessor communication. Now, in the next 20 minutes or so, I would like to share some industry trends with you and try to explain why there is such a resurgence of FPGA in the news, in the media lately. And then I will pass it on to our guest speaker from Amazon Web Services. So as everybody here knows, processor frequency scaling stopped about 10 years ago, 10, 12 years ago. And since then, processors moved to multi-core architecture, but that also hit the same problem. And the problem really is that there are too many transistors switching at the same time, and current leakage at small geometries is hitting the power constraint limits. However, at the same time, workload demand in the data center and at the edge is continuing to increase exponentially. For example, in the cloud, there is a huge demand on video transcoding with things like YouTube, Netflix, Amazon Prime, Facebook Live, etc., which not only require high performance, but also low latency when it's live. And the same goes at the edge. We have similar workloads, video, data analytics, etc., at the edge for automotive, smart cities, and so on. So processor speed is not scaling, but workload demand for speed and latency is continuing to grow exponentially. So obviously, there is a need out there for accelerators, for application-specific accelerator. You need acceleration for video, you need acceleration for AI, machine learning, you need acceleration for search, etc., etc. The problem is, it only makes sense to create application-specific accelerators if there are a few killer apps out there that can justify building ASICs for accelerator. And unfortunately, that's not the case. What I'm showing here is from a paper from Google, where they analyzed their own workloads in their own data center over a period of 4 years. And you know that Google seems to have a few killer apps, right? Like search, for example, or video transcoding for YouTube. However, what they found out is that their hottest app, which is probably either search or video transcoding related, their hottest app only takes 9.9% of their entire CPU cycles in their data center. That's the hottest one. After that, it goes down. So you see the cumulative graph there, and you can see that their top 50 workloads are taking less than 60% of their CPU cycles. And what they also found out in this same paper, you can see the title and the authors there, by the way. You can Google it. You'll find it. Some of the authors are no longer at Google, but they were all at Google when the paper was written. So what they also found out in this paper is that on year one, the top 50 workloads were covering 80% of the CPU cycles. And it went down and down and down year after year. And on year 4, as you can see, it's taking less than 60%. So what they're saying is that workloads are becoming increasingly more diverse. And they're changing more rapidly as well. So really, there's no possibility to build application-specific accelerators, even for video. You build an accelerator for HEVC, well, HEVC spec changes, and some people need high quality, some people need high speed or low latency, and then now there is VP9, and then it's going to be followed by AV1. It keeps on changing really quickly. So what this means is that reconfigurable accelerators are pretty much the only option left for this kind of workload. And this trend is also valid at the edge. So we used to have a lot of workload running at the edge, like set-top boxes or cameras for surveillance, which are starting to move to the cloud. The compute part is moving to the cloud. But then with increasing speed of edge devices, these workloads are coming back partly to the edge. For example, for camera surveillance, it totally moved from the cloud to the edge, but then streaming the video all the time, 24/7 to the cloud didn't make too much sense. So now there is some pre-processing that's happening at the edge, and only the clips that are meaningful are streamed to the cloud. So what I'm saying here is that you have very similar workload moving from cloud to edge and edge to cloud. So you do need reconfigurable accelerator on the cloud, but you need devices that you can also bring to the edge to run the same workloads. And that's where really where FPGAs and Zinc SoCs come into play. They have basically configurable processing subsystems and configurable hardware that can be dynamically reconfigured to create custom accelerators. And their key advantages, really, I mean, you're all FPGA savvy, but the key advantages of FPGAs are that you can build your own custom data flow graph, which is customized to your application with your own custom memory hierarchy. And that's really maybe the biggest advantage. Your custom memory hierarchy lets you keep the data internal to your pipeline instead of going back and forth like a von Neumann machine to DDR. And for edge devices especially, custom IOs is a big thing, obviously, for sensor fusion. But the problem is, how do you program those, right? I think you all would agree that FPGAs have not been the easiest device to program out there compared to CPUs, for example. And what you will learn today throughout the day and in the 3 tracks is that Xilinx and its partner are providing a richer development stack so that hardware designers, but also embedded software developers and even application software developers can program them fairly easily with a development stack that they're familiar with. And that comes with a breakthrough and a roadmap that we've been working on in the past 6 or 7 years. As you know, we released Vivado at the baseline of that roadmap about 6 years ago. And that's for the RTL developer, the hardware developers. And we have basically completely retooled everything we have. We wrote everything from scratch because we were designing multi-million lot FPGAs and Xilinx SoCs. So Vivado gave us a very solid baseline for that. But at the same time, we were working on building higher level tools. HLX, which was released about a couple years after Vivado, basically enables hardware developers to develop functions in C and then package them and drag and drop them into IP integrator and connect them to each other and connect them to connectivity IPs, IP subsystems. This is really one step towards software programmability because you can design your functions and simulate them in C. That's a big thing because if you're doing video processing today, for example, if you want to simulate something like that in RTL, it would take days to simulate, whereas it takes seconds to simulate in C. So that's where the 15x productivity on the slide comes from, and that's quoting customers who are using the HLX methodology, HLS and IPI. And then on top of that, we have built what we call the SDX tools, SD Accel and SD SoC, which basically enable full software programmability of FPGAs and Xilinx SoCs, given that the software developer has a board with an FPGA or a Xilinx on it, with the I/O connectivity and the software stack already provided. And we didn't stop there for SDX. We're basically providing the entire software development stack because when you give a software development tool to a software developer, they go, okay, where is my linear algebra library? Where is my math.h? Where is my machine learning framework? And so on and so on. And we cannot ask them to develop all that, right, and accelerate it on the programmable hardware. So Xilinx and our partners are working on building this stack. So we already have OpenCV for computer vision. We're starting to have different machine learning libraries. And we use those to accelerate industry standard frameworks like CAFE, for example, or MXNet for machine learning, or FFmpeg for video transcoding. Storm, we have customers who have accelerated Apache Storm for streaming analytics, and GATK for the genomic toolkits. And actually, developers like you are needed from by the software users. So they need you to accelerate software frameworks like that or software APIs. And I will give you more examples of customers and partners who have done that, and some of them are demonstrating what they have done outside. And the other thing is that this stack is now available on the cloud. So it's not that you're going to accelerate those frameworks for a specific FPGA card or a embedded Xilinx SoC card. You can also do it on the cloud, and that would help you move your business model from selling hardware appliances and shipping expensive hardware appliances to just selling a software API on the cloud. And a lot of our customers have started to do that transition, and it really accelerates, for example, their sales cycles from months to build and ship a hardware appliance to literally minutes to provide the software API and say, here, you can evaluate it, and if you like it, you pay for it, and you pay per use. So this is the FPGA as a service business model that the stack is enabling. And you can see that we have our FPGAs in 6 different data centers today, 4 of them being hyperscalers. It's really Nimbix and AWS who have pioneered FPGA as a service. And since then, we have had announcements from Alibaba, Huawei, Baidu, and Tencent as well. So what that means is that you have the latest and greatest Xilinx FPGA on your desk right now at the click of a mouse. If you have a laptop, you have the latest Xilinx FPGA at the click of a mouse on the cloud. And you can either use it for a accelerated software or develop an accelerator on it. And this is what FPGA as a service is enabling today. We have a partner, DeFi, who's one of the ones demoing out there, who is accelerating speech recognition on AWS, and they're getting a 40x acceleration compared to CPUs. NG codec accelerates video transcoding. And for HEVC encoding, they get a 10x acceleration, which means that what 10 Xeon servers can do, they can do it with one F1 instance, which is the FPGA instance attached to a single Xeon server. Genomics is probably one of the best targets for FPGA acceleration, just because it's full of bit shuffling and custom pipeline. And Edico Genome, which is one of our partners there, is getting 100x acceleration. They basically go, as you can see, from 33 hours to analyze a human genome to 20 minutes, CPU versus FPGAs. And by the way, GPUs don't even play in those domains. Their architecture is just not fit for genomics or video transcoding or data analytics. And for data analytics, we have a partner, Rift, who also has an application on the AWS marketplace. And they're accelerating software like Elasticsearch, Splunk, Tableau, and so on. And they get about a 90x acceleration. Again, bit shuffling, custom width, custom pipeline, custom memory hierarchy. That's what's doing it. And they're getting, for example, 40 minutes instead of 60 hours to analyze a terabyte plus log file with Elasticsearch. So our next speaker will cover in more detail those applications, but there is one that I wanted to highlight. It's the Edico Genome one. I especially like this one because they use FPGA acceleration to save lives. They save babies in children's hospitals. The use case here is that when babies are born and you see that they're critically ill, hospitals want to do a quick genome analytics to see what the cause of the illness is so they can cure them. And the entire genome analysis from scratch for a human, for a baby, used to take over 2 days. So they were losing a lot of babies during that time. And a couple years ago, Edico Genome came up with a hardware appliance where they didn't have FPGAs on the cloud yet. And they managed to accelerate with Xilinx FPGAs. They accelerated the analysis part of the genome sequencing by 100x, basically taking it from 33 hours to 20 minutes. Basically, they shaved over a day from the entire process, saving babies. And they got a Guinness World Record for that. And recently, just a few months ago, they got another Guinness World Record where they analyzed 1,000 human genome in 25 minutes on AWS using the F1 instance. And that was with the Philadelphia Children's Hospital. The first one was with the Rady Children's Hospital in San Diego. So they have obviously an application on the AWS marketplace, and they're getting usage every single day from hospitals. So that was on the cloud. On the edge part, our same machine learning partner, DeFi, is accelerating machine learning for applications in automotive, in smart city surveillance, for drones, and so on. And the example here is about smart city surveillance. They're getting about 5x the performance of embedded GPUs. And again, they're getting that kind of performance for the same reasons, custom memory hierarchy, custom data flow, but also because they're able to trim the neural network to the specific needs of that application. And by trimming the neural network, it allows them to put more compute into the same device. So they get better accuracy and 5x the performance of a GPU. You can talk to them today. Again, they have a booth here. So you can see that Xilinx is not just about hardware engineer anymore. We're still obviously covering our bread and butter, which is hardware design, but you can see that Xilinx and our partners are providing a richer software development stack to enable software development. And that's not just on FPGA cards and SoC cards, but it's also on the cloud with FPGA as a service. And we also work with industry and open source community to provide all the embedded software that are available out there. Again, that includes embedded Linux, multimedia framework, interprocessor communication, low power management, and so on and so on. So to list the partners that are out there so you can see who they are, I have this slide. There are about, 14 plus Xilinx, 15 different tables out there. Just to cover a few of them, AWS and Huawei, you can talk to them for FPGA as a service. Avnet and Silica, you know them. They're demonstrating multiple things, including machine learning. DeFi is demonstrating machine learning. And again, they have that solution both on the cloud and the edge. Titan IC is one of the developers that has an application on the AWS marketplace, so you can talk to them to see what their experience was. Agios specializes in power management for embedded software, and I let you discover everybody else on that slide. So again, we want you to learn about these tools and methodologies, and I encourage you to go to the track that you're the most interested in. Again, hardware, application software, and embedded software developer track. The application software developer track will split into two after lunch. We will have an edge software development and a cloud software development. But until lunch, it's going to be one track.